I'd like to invite all the speakers once again for the panel discussion. But before we get started, I just wanted to do a very brief demo of the ClimateNet project. This is something that Jebb alluded to in his talk, which is essentially a labeling tool for earth sciences applications. This is one way of generating training data for these deep neural network models. So I'm going to share my screen in a moment and show you what the ClimateNet project is about and how you might use this labeling tool for your research. All right, so I just wanted to introduce ClimateNet, which is a project that we've launched at Lawrence Berkeley Lab. This is essentially to create human-labeled, expert-labeled data sets for various different deep learning applications. I'll post links to the webpage and the description of the project on the Slack channels. So feel free to take a look and explore. We're always looking for people to contribute labels to these large data sets. So you're welcome to play with the tool. We've gone through a lot of the basics in previous talks, so I'll skip all of that and go straight to the tool. Jebb mentioned this during his talk. And this is the interface called Climate Contours. It's based off of MIT's computer vision lab. They had a labeling interface for natural images, and we adapted it for climate data. What you're seeing here is global climate model output at 25 kilometers resolution that's been uploaded into the tool. We have various different channels here. The focus of this project is on labeling extreme weather phenomena, such as hurricanes, atmospheric rivers, weather fronts, and various other weather patterns. You can look at these patterns on the tool and then essentially go and label these patterns. You can toggle between different channels. For example, here we're looking at the water vapor fields, the integrated water vapor. IVT, which was introduced earlier, is a vapor transport variable, which is also useful for atmospheric rivers and other phenomena. You can look at the wind fields, for example, pressure at sea level, which is useful to determine tropical cyclones and combinations of these variables. So just to very quickly show you what it looks like, the labeling would be something like this, where you basically draw a polygon around a particular phenomenon of interest. In this case, it's a tropical cyclone that's approaching the southeast of the US. So you can label it as a tropical cyclone with, say, high confidence, because we clearly see that this is a TC. And when you're done, you click on done, and it gets registered on the right as one of the labels. You could do the same for an atmospheric river. So for example, here off the coast of Western Australia, this looks to be an AR. So you could go about labeling it in this fashion. So this is just a very brief introduction. I encourage you to play with the tool and ask me questions if you like. This is one way of essentially augmenting data sets that exist for training these deep neural networks. This could complement your heuristics, or it could be a whole different approach to labeling data. All right, with that, I'm going to invite our panel members to join us again, and we can get started with questions that the audience has on Slido. Thank you.
Oh, Sue, I think you're muted.
Sue, I think you're muted.
Thank you for pointing that out, Karthik. I was gabbing away. I'm answering the question, why would one want to perform nowcasting? And that is a really good question. For integrating renewable energy, if you're sitting at a grid operator's platform, it's their job to know when to bring in each of the type of unit. So for instance, if there's going to be a lot of wind coming in the next hour The grid operators would then tell, say, the coal units to decrease their output to leave room for that wind at the time. If the wind or the solar is expected to go down in 2 hours from now, then they're going to have to make sure that there's some combined cycle gas online to quickly cover that. So it's very important in many operational cases to have that type of information over the very short range. And by nowcasting, I was using that to mean from basically current out to about 6 hours. You know, people use slightly different definition of nowcasting, but that's about right.
Okay, so there seems to be a question from Krishna on knowing what we know about machine learning and AI, why would ML or AI perform better used independently or by a hybrid approach?
I'll go ahead and take that one as well. I assume what is meant here is by independently using a machine learning technique alone, such as we did for some of our StatCast applications, where we want that short-term information. When there is model information available, however, it usually is really helpful to bring that information into the forecast. For instance, when we're running NWP models and correcting them with Diecast, we often use the Diecast forecast as an input to a shorter range forecast with machine learning. So oftentimes it's very beneficial to blend multiple methods and to use the tools available to the extent that they each work well. Blending them produces a better result.
Yeah, I agree with that. I guess I would just add, we're thinking about that in the climate modeling space as well, how we can hybridize these techniques and do more physics-informed machine learning parameterizations. And I think this is going to be discussed in more detail later this week, but I think it's an important question. And it's something that I'm certainly more interested in learning more about, these possible hybrid approaches.
So perhaps relatedly, there's a question on some fundamental books and articles related to AI and machine learning applications in the earth sciences. Based on your experience, do you have any recommendations?
Well, a first one that was written actually in 2009 came out of the AMS AI committee at the time. It was an edited book with contributions from many authors. And for that point in time, it really was covering a lot of the types of applications that were being done. It's applications of artificial intelligence in the environmental sciences. I was one of the editors together with Karen Marsban and Antonello Piccini. Nowadays, there are lots of articles. If you peruse the literature, whether it be AMS journals or specialty journals, there are lots of articles on AI applications. Each particular application area seems to be coming out with books. You know, for instance, in energy, there's a book, Weather Matters for Energy, and there's chapters in that about AI approaches. So it's becoming prevalent and rather easy to find. If people ping me at my email address, haupt@ucar.edu, I'll be glad to send DOI connections for those.
Yeah, I guess from my experience, I relied on books more for the fundamentals of machine learning, some of the references that Dorit mentioned in her talk, more about the statistical background. And then for applications specific to earth science, I found articles to be just more helpful or more relevant. And again, we could probably come up with a list of some of those specific to those applications. But then the other thing I found was just blog posts, especially like applying neural network emulators and how to do the training process and how to think about hyperparameter optimization. That was a lot of just like people posting about their experiences and reading and getting some code examples online.
One more area I would suggest. Oh,
sorry, go ahead.
Go ahead, Karthik. One more area I would suggest is that, you know, with an AGU or AMS or your field diverse sciences, that there's a lot of growing conferences around AI and ML techniques. And so going back through past pre-prints for conferences, you might be able to find related papers. They can point you in the direction of other materials to read as well.
Just to add to that, David did send out a list of recommended readings before the school. We highly encourage you to look into that as well. That has a list of books for fundamental AI and machine learning background, and also a deep learning textbook. I mentioned that during my talk yesterday. I also want to mention that Wiley, the publishers, are coming out with another updated version of the most recent AI and machine learning applications in the earth sciences. I think the editors are Gustav Campbellis and others. So do keep an eye out for that book. Should be released sometime this year.
Okay.
All right, so sorry, that's it.
Okay, Sushant Kumar is asking about the code for Diecast and whether it's available. That code specifically is not available because it was originally generated for a commercial entity. The IP for that is held jointly with that commercial entity, so it cannot directly be released. However, we have built some other codes, such as the StatCast code, as well as some more recent blending codes that are made open source. And those are available on UCAR wikis. Looks like somebody's asking specifically about ramp-up events. And again, that's a very challenging area, as noted here. The StatCast tools are some of our best tools for that, particularly a version that brought in some satellite data. And although we don't make the Diecast code available, we publish details openly, and you know, people are welcome to use those techniques.
So the next one is very general. What are the most popular frameworks for these types of research, Keras, PyTorch, etc.? What are your personal experiences with that?
Well, yeah, I mentioned in my talk, I used Keras and TensorFlow, and I was able to find nice examples and documentation. And that's kind of why I went that route. But I've also heard a lot of folks using PyTorch. So I think I'm not sure which one is more popular, but I think they're both pretty common.
Yeah, yesterday we had David describe his work with PyTorch. So yeah, it does seem like there's a lot of competing frameworks today, and there's many examples of applications with all of these. So you're welcome to try them out and see what works best for your particular problem. So the next question was, if you are using neural networks to ascertain the CLM model parameter uncertainty, why do you use the CLM output to generate training data instead of observed data?
Right, yeah, this is definitely a question for me. So I saw this question and I saw that there was a reply to it as well. And I think the reply is similar to what I would say, in that, you know, the goal here was really to build an emulator for CLM for the land surface model. So we needed to use the output as part of the training. And again, we were doing this in a supervised context. So we had a particular set of parameter values that we knew, and we knew which model simulation was associated with each of those parameter values. And so the goal was really to emulate that process. And then the next step is then to bring in the observations and to say, okay, now that we have this fast emulator, let's compare the results of the emulator, the predictions with the observations, and be able to better constrain parameter values this way. But I'm happy to follow up more if there are further questions on this.
There's one that's probably for you as well, Katie, that's kind of specific. For the land surface model, did you consider different layers of soil moisture?
Yeah, absolutely. CLM considers soil moisture at varying layers, varying depths across the globe. So that's absolutely built into the process model, and the level of complexity and detail that we're simulating with CLM is the ability to simulate soil moisture at different layers in the soil, different depths, and also the vertical transport of moisture throughout the soil.
The next one is probably for you, Sue. How does the CI forecast using only satellite data compare to high resolution model output? And how might you include the model output into the machine learning process?
Okay, good. So typically on the very short ranges, the satellite data is better once you get past its latency period, which even for the GOES is only about 15 minutes or less right now. So that was really quite good, but it drops off because the satellite data information alone doesn't allow for cloud formation and dissipation. So at some point, the other methods start improving on that. Now the HER does allow that type of information. It also assimilates satellite data, so it usually does pretty well. But it has a longer latency. So, you know, until about 45 minutes or so, you may not have that HER data available. So the sweet spot for the machine learning really is that very short time frame. And it even gets better when you bring satellite data into it, as we did in a couple of test cases.
Yeah, that's what I was going to say. This goes back to that hybrid approach where you bring in data from multiple sources from the HER and satellite, and you probably strengthen the results.
Mm-hmm. Great.
So the next one is, what's the difference between weather forecasts and Diecast? How reliable are the Diecasts?
Okay, so, and that depends where you're getting your weather forecasts. If you're getting your weather forecast from some of the apps, for instance, those of IBM Weather Company, you are getting them from Diecast. So in that sense, the weather forecasts that you're getting from Diecast are very reliable. Diecast has been tested against lots of different types of techniques. It usually is as good as or better than most. You know, not to say it's the only machine learning method out there that doesn't add value, but typically machine learning on top of numerical weather prediction does add value.
Okay, the next one is, have you tested how your 100 simulation resolution impact on your final results for machine learning?
This might be a question for me. Yeah, I mean, yeah, it would be interesting to test with a larger amount of training data. And, you know, one thing I could do is I have the large out of sample test where I ran a second 100-member ensemble, so I could use information from that to inform the emulator, and I've thought about doing that. Oh, maybe this question is about spatial resolution of the model itself. I'm just thinking now it says resolution impact, and I haven't tested that, but that's a really good question. And like I said, the particular configuration of the climate model is going to inform the results, but also how computationally efficient it is. So we chose a particular configuration of the land surface model uncoupled from the rest of the climate model, so forced by an atmospheric reanalysis forcing, and a particularly low resolution, so 4 by 5 degree horizontal resolution, which is particularly low for climate model, but run globally. So there's always trade-offs with resolution and complexity and speed. So it would be interesting to look at different resolutions and how the results compare.
All right, so the next one's an interesting one. How do you use satellite images and deep learning techniques to predict hurricane track and intensity?
I'm sure I've seen presentations and papers on this, but it's hard for me to talk to it directly. Jebb, are you there? Are you aware of work?
Looks like Jebb might have dropped off.
Yeah, David John, you came on, but you're muted.
Yeah, I can say there's a really good paper by Wimmers et al. From 2019 where they're using I think microwave imagery to estimate hurricane intensity. So they weren't necessarily doing prediction, but they were trying to improve on something called the Dvorak technique, which is kind of the standard for looking at a satellite image of a hurricane or a typhoon or other tropical cyclone and estimating intensity. And they were actually even able to do some uncertainty quantification and interpretation with it. So that was a really good result. There's also been a number of I think there's some other work at CSU with I think it was Chris Slocum who's been working on trying to I think use like geostationary satellite imagery and then use a neural network, or actually I think they use like a random forest model to map it to a like what the microwave version of it would be. I don't quote me on those details because I think there's probably some incorrectness in there, but if you search around for it, you might be able to find some more results. I'm currently working on a project with using deep learning and HWRF data to do kind of a bias corrected hurricane intensity prediction, and gotten some promising results, but it's not published, and we're going to be running it in real time. And there's a number of other groups. There was a group in South Korea that also did combined track and intensity prediction. It's there's a big session at the AMSAI conference back in January 2020 where we actually had 2 tropical cyclone and AI sessions. So I recommend checking if you want to learn more. Go to the AMS annual meeting website and check out the program. All the talks have been recorded, so you'll find more information there and some of the latest and greatest work going on.
Jebb is back, so maybe I'll repeat the question in case he has anything to add to that. So we're looking at the second question displayed, which is how do you use satellite images and deep learning to predict hurricane track and intensity? So if you have any thoughts on that, Jebb.
Yeah, there's quite a few efforts, I think, ongoing looking into predicting hurricane track and intensity. I think it's an interesting challenge. I think a lot of people are interested in rapid intensification, but in terms of when we talk about data and labeling data, the number of storms that go through that rapid intensification process are rather limited. So we don't have a whole lot of data to go off on for that. And I think what David mentioned about combining the forecast from H4 along with deep learning to look at and improve hurricane tracking and intensity, I think is a common course. We see a lot of different people looking into those techniques to help improve beyond existing methods. So I don't have experience myself directly, and I know there's quite a few people, I think, up at CSU as well as through NESDIS and AOML within NOAA. Quite a few different groups are looking into that capability.
Thank you. So the next top question is, how do you use AI, machine learning, and deep learning for long-term predictions, for example, on decadal timescales?
That's a really interesting question. That's a hard question because prediction on decadal timescales, we have fewer data sets available that are big enough for some of the machine learning methods. There are people working on it. There's more people proposing ways to work on it. My team, for instance, looked at climate change, potential changes in wind and solar resource by basing it off climate models, training on historical climate runs, and then applying the prediction on future climate runs. The same is being done on the decadal scales. Again, there's a lot happening. I think there was some discussion of that also at the 2020 AMS meeting.
Yeah, I'll just add that I guess one of the challenges with long-term prediction is changing the nature of the relationships that we're trying to predict. I mean, when we're training, for example, on present day or historical climate information, how well do those relationships hold up in the future? So that's something that we're thinking about at NCAR with some of the feature detection work for extreme events. Can we then extrapolate to the future climate? Another example, which I think I saw a question on S2S, seasonal to subseasonal prediction. So more on that time scale, I know that there's been some work on trying to use deep learning to predict El Nino, maybe on like a couple months to a couple years time scale. So that could be an interesting area of bringing in some of the deep learning techniques, especially when you can then do some interpretation on your results and actually figure out what, spatially where you're getting the most skill for an ENSO prediction. Is it, just in the tropical Pacific, or is it other parts of the globe? So Yugun Ham has a nice paper, deep learning for multi-year ENSO forecasts. There's probably others though.
Just related to that, I must mention that one of our hackathon problems is exactly on ENSO prediction at the seasonal time scale. So if you're interested, do check out that problem as well if you're not already working on it. All right, so the next question is on, are there other machine learning techniques beyond CNNs that would make sense for a project like the hail prediction, or is it a priori the best choice?
Okay, great question. There's been lots of techniques tried. David John did a PhD dissertation some years ago about that. I'll let him chime in with the results of that.
Yeah, so I worked on putting together a hail prediction system during my PhD using random forest, and along the way we tested a number of other methods, gradient boosting and linear regression, and they all do pretty well. Random forest seems to be fairly robust. We got funding from myself and other colleagues at the University of Oklahoma, including Nate Snook, Amy McGovern, Amanda Burke. We got two NOAA Joint Technology Transfer Initiative grants to basically move the algorithms toward operations, and we've been testing it in real time as part of the hazardous weather testbed spring experiment. Basically made various tweaks along the way. This year we started testing out a CNN approach as a kind of real-time prediction system, and it's showing some promise, but like the first version of it didn't actually outperform the random forest in terms of like the verification, but it's still kind of in its early stages, and we're working on refining it. The random forest just is a fairly robust algorithm and easy to tune, and so for a lot of problems, it's like it's often I call it the second best algorithm for everything, because you can always tune something else a lot more and get somewhat better results, but out of the box random forest works pretty well on a lot of things. There's been other groups that have also implemented random forest severe weather prediction systems, including Greg Herman at CSU. When he was at CSU, he's no longer there. He's at Amazon, and Russ Schumacher's group. Eric Loken at University of Oklahoma has also implemented a system, and then Ryan Sobash at NCAR has also built one that does like general severe hazard prediction of random forest and a kind of feed forward neural network that they all run in real time. They all seem to be doing pretty well. So it's multiple groups have found it to be a pretty robust algorithm across different data sets, different model ensembles. I'd like to see more CNN work done in the real-time operations, and we're also looking at ways you can use the interpretation parts to build other analysis tools with it.
Thank you. We'll take probably one or two more questions before we close. There's one that's really interesting. How do you need to keep updating the optimal parameters, for example, with new observations to be applicable for projections into future climates?
Yeah, this is a great question. Yeah, thanks for this question. I think, you know, for our specific problem, we intentionally chose parameters that shouldn't vary to a great extent in a future climate, and that we think that those relationships are going to be fairly constant just based on the how the parameters work and the construction of the model. But for sure, that's somewhat of an assumption, and we need to think about how we're thinking about those relationships going forward. I think it also relates to the conversation we were just having about prediction.
And in the problem I mentioned, where we were looking at estimating changes in wind and solar radiation over climate scales, we actually made a trend line based on past performance and used that trend line to update our calculations, especially when we were using temperature as one of our predictive variables. Now, of course, that trend line itself is going to need updated regularly as well. So it is a good point that in a dynamic system, you're going to have to be able to update your parameters dynamically.
All right, we'll take one last question before we close. The one on data imbalance seems interesting. Can you describe what data imbalance is and how you might get around it? Any takers?
So I can take on this one. So the data imbalance is a problem where you want to have a kind of an equitable distribution of your different segmentation classes or even classification classes when training a machine learning network. Otherwise, the underrepresentation, it may not get an accurate prediction of those particular types of classes. So data imbalance is that case when you have, you know, if you had cats and dogs, and if you were trying to classify between the two, if you had 90% of your images were cats and 10% were dogs, the tendency of your model would be to predict cats because the cats can be right 90% of the time, which goes into the accuracy. So I mentioned this in my slides, but there's a couple ways around the data imbalance problem. One is the loss function, looking at the loss function. You can do different weighting techniques to weight one class over others, or even pass in its representative levels within your training set, so they can better understand and better weight the differences between those to have a good trained model even with the data set imbalance. The other way is to do techniques that are either undersampling or oversampling. So you can undersample a dominant class. By that I mean, if in my example of cats and dogs, 90% of the images are cats, you can undersample that so that more matches the representation you have for the dogs. Or you can oversample, send more of the dogs through in your batches so that it has more representation as part of that. But that's for more of the classification techniques. When you're looking with segmentation, it's the number of pixels in a particular image, and so you don't have those options available to you. So it's better off to maybe use some of the loss functions. Others might have opinions on this too.
Yeah, that was pretty comprehensive. So maybe we'll pause there.